Welcome. Today we'll be discussing fog computing in a manufacturing environment. My name is Andres Castillo, and this is for class ICTN 6875, Emerging Technologies. In our discussion, we will cover the following: the evolution of cloud computing and the industrial Internet of Things. We'll define fog computing, review some of the benefits of fog computing architecture and some of the challenges to the design. And at the end, we'll have some resources. The evolution of cloud computing and the industrial Internet of Things. In order to understand fog computing, we must first understand how the platform is an evolution of cloud computing and the Internet of Things. So what is cloud computing? Cloud computing is a configuration of remote hosted servers storing, processing, and collecting data over the Internet. Some benefits of cloud computing include scalability and cost savings. So for an example, a global manufacturing company decides to deploy an application worldwide. The data collected for this application will be consolidated and archived for analysis and reporting information which will affect business decisions and the manufacturing production for several plants. If each plant were responsible for purchasing software, hardware, a copy of the application, database licensing and maintenance, and all these things are necessary to deploy the application, there is a potential for high overhead costs and inconsistency of data output. Each site would be independent of the others. Application configuration, system configuration, support models, disaster recovery plans, and support resources would be multiplied across the domain. As an alternative, the corporation determines a data center, which can be configured either through internal or external sources, is needed to centrally house the application and the database servers. As the data is collected and transmitted from the plant over the private wide area network to the data center, it can provide a consolidated view for analysis of multiple locations in a matter of minutes. Maintenance systems support and application support can be managed centrally with a centralized configuration, which also would provide cost savings for the company as a whole. Deploying the application client is also centrally managed and provides the ability to rapidly distribute the application to multiple endpoints simultaneously. Not only is the potential for the cost savings in licensing, support, and maintenance, but application and availability disaster recovery plans are now centrally managed. Some examples of cloud computing in manufacturing. In a pharmaceutical manufacturing plant, there are several applications collecting data from chemical lab instruments connected to PCs or directly connected to the network, ensuring the quality and efficacy of the product. The collected data is required for producing records and for batch information and adherence to quality standards, and for evidence to the Food and Drug Administration that it was documented, consistent, and safe. The data is then transmitted across the WAN to a centralized repository or data center somewhere off-site, which is then analyzed and archived and used for reporting and oversight. So management from across the globe now has access to this live data from any location in the domain. Another example, more common to most manufacturing facilities, relates to the IIoT devices, which is the industrial Internet of Things. The original term of Internet of Things refers to any device other than the typical laptop or PC connected to the Internet. For example, cell phones, cars, household appliances, OnStar, and anything else that can communicate with the Internet. Manufacturing plants have been around for many decades, so some still maintain the original equipment they purchased over 20 years ago. And within the production infrastructure, there are devices to monitor, manage, and control production machinery, monitor environmental controls, record production information, and identify potential issues in production machinery. These devices have gradually migrated onto the local area network. And now, rather than individuals walking to each point and manually recording data, data now flows to a centralized data historian. Multiple endpoints transmit the information over the LAN and in some cases over the WAN. Devices can either be hardwired or use wireless connections to the network. As manufacturing processes improve, we see upgrades from legacy hardware to modern equipment pre-configured for network connections, working in conjunction with application hardware and software for centralized data collection. So, a term now describing the newly connected devices is now called the industrial Internet of Things. Information is collected from programmable logic controllers, PLCs, from sensors, over a supervisory controlled data acquisition system, or SCADA system, and which is used to manage PLCs, sensors, actuators, and environmental sensors. Within the diagram, we see various levels of typical IoT structures. At the bottom level, you can see the endpoint devices, and moving on up to the zone gateways, which is the level of just some switching. Then you continue up the ladder to show through the connected fiber and the interzone gateways, and then the enterprise network, which then leads you to the enterprise-wide application, as well as the WAN. The design provides a general overview of cloud computing and the industrial Internet of Things. So now that we have a basic understanding of cloud computing and IoT, we can move forward to fog computing. So as a result of rapid growth of the Internet of Things, a group of companies collaborated and formed what's now called the Open Fog Consortium. This was created in 2015 by founding members Cisco, Dell, Intel, Microsoft, ARM, and Princeton University. It was formed to create a standardized IoT networking format to allow endpoints to communicate in a secure and private architecture. These companies had the foresight to see the rapidly expanding growth and data transmission over the Internet, which is currently happening in an inefficient format and would require a standardized computing structure. It is projected that literally billions of devices from around the globe will eventually connect to the Internet. So this standardization is working towards reducing Internet traffic, ensuring security, and accelerating IoT communications. So let's get on to fog computing. As stated previously, fog computing evolved from the concept of cloud computing and is used to enhance, not replace, the architecture. The term fog computing is generally associated with Cisco and refers to bringing the cloud down to the ground level. So in other words, bringing the cloud closer to where the data is initiated. So let's take an overview of some of the basic concepts. According to Jacob Pizon and Jerzy Lipsky in an article written for Applied Computer Science, fog computing is a highly virtualized platform that provides compute, storage, and network services between the devices and the traditional cloud computing data centers, typically but not exclusively located at the edge network. Normally, a network edge switch or an unmanaged switch would be at that level, right next to the initiating device. and neither of which of those switches has the capability to compute the received data. So they're just merely traffic cops and pushing the information through. So as far as addressing the need, the article further discusses how some of the data transmitted from the device may not be necessary for the data collector at the other end of the hierarchy. Reducing traffic by removing packets of extraneous information can greatly reduce bandwidth utilization. So as transactions occur, the fog device closest to the sensor begins the process of analyzing data and determining which packets will proceed to the next level. These transactions occur extremely fast, as in milliseconds and subseconds. So depending on the equipment requirement, some of the devices I've seen process about 10 collections per second, and depending on the network configuration, can be affected by latency. So latency is the time interval between the data, when the data was initiated and when it was received. Data transmission through several layers of network devices has the potential to drop a packet or two. And if there's a switch that went down and the routing compensated with a redundant path, potentially there could be a gap of data and in the data historian, showing up in the data historian with some time and data loss. So because the fog architecture initiates computing right after the device, latency is reduced and the initial data has been analyzed. So it reduces, and then the data packets and the remaining essential portions of the information is then sent forward for data collection. In an article written for the Journal of Manufacturing Systems, the authors state, as opposed to cloud computing, computationally intensive workloads such as training large data sets and visualizing data analytics are conducted in fog computing at locations where large volumes of data are collected and stored instead of centralized cloud storage. So essentially, the device, as you see on the diagram here, shows the fog device right near the point of data collection. So the information immediately goes to the fog device, and there's some redundancies or paths that are set up, but that device sends that information, and the fog device in turn sends it back or processes it and with some intelligence, and then sends it back to either the PLC or whatever device is controlling wherever it's necessary to go. So some examples of practical applications. In a production, if a packet of data is dropped, it could potentially show a gap in data collection. Every gap has to be investigated and determined whether the cause is of concern or not, and if the corrective action needs to be initiated. So control decisions are also made from the data collected within a manufacturing line. It could determine whether there is a potential problem with the line, or sound an alarm to stop production, reducing the loss of product, or does the data computations at the earliest level, which allows automation to react in a more efficient manner. So here we see a Cisco diagram of the field area networks, and in essence, I'm not trying to promote Cisco, but they have been the initiators of the fog computing diagrams and architecture. They have been at the forefront, also with starting up with the OpenFog Consortium. And within the diagram, you can see the integration of fog devices as compared to the previous diagram of cloud computing. Although there are similarities with the two architectures, the actual layers that are represented by the Cisco IR500 and the Cisco Ethernet WiMAX Wi-Fi hardware. These two devices of networking / computing equipment reveal the incorporation of both wired and wireless configuration and communication to fog devices, revealing the versatility of the collection of data. So what you have are the additional devices within these layers, and I looked up the Cisco IR500, and it references how it processes the data, and it also works with historical um, systems as well, able to communicate and converse with those programming languages. So with that, an important piece to consider is the legacy manufacturing equipment and the inconsistency of vendor loyalty. So you may have multiple vendors on this network, and all of them need to be able to communicate to this device. So this Cisco IR500 has that capability. So this would allow the FOG architecture to be installed sooner rather than later. So you're not having to wait until some other device is upgraded and becomes compatible with the Cisco IR500. It's there. It already is. So the diagram also reveals the complexity of the data traffic to travel from the initiator to the data historian. So you see how the traffic can flow, and it's better to have decisions made at an earlier point rather than at a later point, transmitting data and all the way through, possibly getting to the historian with some packet loss. So here we have some device examples, and I just wanted to kind of give you some quick images, understanding how the SCADA network is set up and how it incorporates computers and the PLCs, and which are controlling also the monitors and the sensors, and then you have an image of an HMI diagram, which is the GUI interface for a SCADA system, as well as the tablet and which can be used to access an HMI, and some typical PLCs. So the growth of IoT and IIoT devices, it's expanding at a tremendous rate, and the current architecture has the potential to overcrowd network bandwidth with both useful and not useful information. The increased number of devices will produce latency issues and when using the cloud model alone. As with all technology solutions, newer, faster, and more efficient models are developed constantly to meet the challenges presented. So in comparisons, under comparisons, basically I just wanted to put a side note. Some folks will use the term edge computing as the same as fog computing. So those are actually two similar in concept configurations or architectures by putting the computing closer to the originator, but they have kind of differing solutions. Fog computing, the fog architecture puts the computing power on the network device with the data and is processed and then returned. Edge computing puts the computing power in an appliance as a programmable automation controller. So it's kind of different. There are different opinions on both solutions. You can kind of compare it to if somebody likes Windows OS and then the other person likes Linux. There are pros and cons in both areas. And it just becomes a matter of opinion and what becomes pertinent for your environment. In an article written by Margaret Rouse, she identified a list of pros and cons to fog computing. So, as part of the benefits, because the intelligence is closer to the device, it reduces the amount of data transmitted to the cloud. It conserves bandwidth. It improves response time, improves security, supports mobility, reduces latency, and these all relate to how once the information is initiated from the device, and the fog device is there to then interpret using intelligence built into it to interpret and determine which bits of information can proceed on through the hierarchy. So as far as challenges for these in a fog environment, you have the physical limitation, which takes away from the anytime, anywhere, any benefit of the cloud. And this was all put together, these benefits and challenges by Ms. Rouse in 2016. And so what she was describing was the physical and virtual location is near the device and not in the cloud, accessible by managers or individuals from anywhere else in the domain. So there are also security issues, such as IP address spoofing, man-on-the-middle attacks, and privacy issues, the availability and cost of the equipment, trust and authentication concerns, and then wireless network security concerns. So there are some possible drawbacks, and depending on your environment, there can be some challenges to make sure that the environment is secure where the device has been located. So in conclusion, we discussed the following: the evolution of cloud computing in the industrial Internet of Things. What is fog computing, which is basically placing the computing intelligence network device closer to the data initiator, with showing some of the benefits as improved bandwidth utilization and decreased latency. Challenges to the design, such as physical location and the device, with possible security issues. And so I have also provided some additional resources. Here's some references from where I received all my information. And then for further discussions, you have the links below. I want to thank you, and I hope you have enjoyed this presentation and learned a little bit more about fog computing.